welcome to lecture series on advanced linear algebra. In my last class, I have defined what is normal operator, and we have seen a special case of the normal operator, that is self-adjoint operator. If it has an eigenvalue, then eigenvalues are real. But the existence of the eigenvectors is we have not answered. Now, let me answer these questions. Suppose if I consider a finite dimensional inner product space, and then my claim is that every self-adjoint operator has a characteristic vector. So, let me prove these results. Let V be a finite dimensional inner product space. Let V be a orthonormal basis for V. Let T be a linear operator on V, and let the matrix representation of T with respect to this order basis B, which is basically orthonormal basis for this space V, equal to, let me consider A matrix. Given T is self-adjoint, that is T equal to T star. So, this implies A also equal to A star. Consider C n cross 1, that is space of all n cross 1 column vectors over the complex plane with standard inner product on C n cross 1. Consider U be a operator, a linear operator on C n cross 1 such that the matrix representations of U with respect to standard basis for C n cross 1 is the A matrix. So, I have considered that matrix representation of capital U with respect to standard basis on C n cross 1 is capital A, and the operator U is defined by U of x equal to A x for all x belongs to C n cross 1. Okay. So, I have defined the operator U, which is basically A multiplied to x. One can easily check, U is a self-adjoint and operator. U is also self, because already we have done for this in our previous lectures, operator defined like this is a self-adjoint. So, that you can follow, or you can take it also homework to check this new operator U on C n cross 1 is a self-adjoint operator. Now, the determinant A minus some C I, if I consider that one, is a polynomial. C I is a polynomial of degree n. This polynomial is reducible to linear factor over the complex plane. So, this implies there exists C belongs to capital C such that A minus C I is singular. So, this implies there exists 0 not equal to capital X belongs to V such that A minus C I x equal to 0, that is A x equal to C x. So, eigenvector of the matrix A exists. So, this implies eigenvector of A exists. This implies eigenvector of U exists. This also implies eigenvector of your given operator T exists. But we know eigenvalues of self-adjoint operator is real. This implies, I mean, all the eigenvalues of the self-adjoint operator are real. So, this implies A minus C I is singular and 0 not equal to x also exists. Here it is important to say here, if it is self-adjoint, then all the eigenvalues are real. So, this implies the characteristic polynomial will have all the coefficient over real. So, in this context, see, I can say if V is defined over real, then the matrix, then the A will also over real R. So, then also there exists a real capital X, I mean entries of the vector x will be over the real number. There exists a real x such that your A x equal to C x. So, in both the cases the existence of eigenvector is guaranteed. See, let me point out 3 more important observation in this proof. First is, for existence of eigenvector of operator T defined over finite dimensional complex inner product space does not depend on the characteristic of T, that is T is self-adjoint. I mean to say, to prove the existence of eigenvector for the operator T defined over finite dimensional complex inner product space, we do not need the concept that T has to be self-adjoint. However, when the finite dimensional inner product space is defined over real, then the concept of self-adjoint is required. Self-adjoint is required to prove the existence of eigenvector. Okay. And third, we have shown the result only for finite dimensional inner product space. If the finite dimensional inner product space is replaced by infinite dimensional inner product space and T be a self-adjoint linear operator on this space, then the operator may not have eigenvector. For example, let V be the space of all complex valued continuous function over the closed interval, say 0 less than equal to t less than equal to 1 with inner product say inner product of any two element f and g, if I define like this 0 to 1 f of t and g of t bar dt, and let capital T be a linear operator on V defined by T of f t equal to simply T into f of t, T into f of t. Okay, this is my inner product, this is my operator. Again I will give you, this is a home assignment, so that it can be shown that T is a self-adjoint operator on the space V. Okay, so that you can prove it as a, consider as a homework. Okay. So now I will show that this operator does not have eigenvector, even though it is defined over an inner product space and it is also self-adjoint, but it does not have any eigenvector. Okay. So suppose T has eigenvalue, say C belongs to capital C and alpha be the corresponding eigenvector, okay, that is T of alpha equal to C alpha. Suppose like this. This implies that, let me consider, okay. So, this is like this thing, T of f equal to C of f, I mean T of f of t equal to C of f, like this thing. So, this is my linear operator. So, 1 and 2 implies, so 1 and 2 implies C into f of t equal to t into f of t. This implies C minus t into f of t equal to 0. So, this implies f of t equal to 0 for t not equal to, but f is continuous. So, this implies f of t equal to 0 for all t belongs to 0 and 1. So, this implies C cannot be an eigenvalue of t, that is t does not have eigenvector. Okay. So, we have seen that if the self-adjoint operator defined over an inner product space, then the operator may not have eigenvectors. Okay, so now let me prove one more nice results. It is like this, let V be a finite dimensional inner product space and let T be a linear operator on V. Suppose W is a subspace of V which is invariant under T, then the orthogonal complement of W is invariant under T stars. So, the proof of this result is very simple, it is like this. We have to show if alpha belongs to W and beta belongs to W complement, then inner product of alpha and T star equal to 0, where T star is basically adjoint of T. Okay. We have inner product of alpha T star beta equal to inner product of T alpha and beta. Okay. So, this is equal to 0 since T alpha belongs to W, as W is invariant under T. So, since W is invariant under T for any element alpha belongs to W, T alpha will be inside of W. So, therefore, inner product of T alpha and beta which belongs to the orthogonal complement of W must be equal to 0. So, this implies what? W complement is invariant under T star. Let me consider another nice results. Okay, so now we are going to prove the semi answer of our question which I raised in my last lecture. That is, if you consider a finite dimensional inner product space and if a T be a linear operator defined on it, then under what conditions the space will have a orthonormal basis which each vector is basically eigenvector of the corresponding operator. To answer that question only we introduce the concept of normal operator, and again we came to this special case, that is self-adjoint operator which is also normal operator. Now we will show that if I consider a self-adjoint operator on a finite dimensional inner product space, then the space has a orthonormal basis which each vector is eigenvector of the self-adjoint operator. So, which is given in this theorem, so it is like this: V be a finite dimensional inner product space and T be a self-adjoint linear operator on V, then there is this orthonormal basis for V, each vector of which is eigenvector for T. This results will prove by induction on dimension of the space. This result will prove by induction on the dimension of the space V. Let the dimension of V be n, which is strictly greater than 0. For n equal to 1, we have, according to our previous results, there exists an eigenvector alpha associated to say some eigenvalue C such that T of alpha equal to C alpha, T of alpha equal to C alpha. Consider alpha 1 equal to alpha by norm of alpha. So, this implies alpha 1 is also an eigenvector of T. Let W be the subspace spanned by alpha 1. So, W is invariant under T. So, according to our last result, W complement will be invariant under T star, that is T, because T equal to T star here. So, the dimension of W is n minus 1. Consider U be a restriction operator, restriction of T on W complement. So, this implies U is a linear operator on W complement. Since T is self-adjoint, then so is U, then U also will be self-adjoint on W complement. So, this implies according to our hypothesis, what is the hypothesis I have considered? I have assumed that suppose the result is true, for any space, inner product space of dimension less than n. So, now we have to prove that result is also true for dimension n. So, since the dimension of W complement is n minus 1, I can assume that the result is true for the operator U, which is defined over a inner product space of dimension n minus 1, definitely will have a orthonormal basis consisting of eigenvector of the operator U. Now, according to hypothesis, the space W complement will have an orthonormal basis where each of vector is eigenvector of U, that is indirectly eigenvector of T. So, let B equal to alpha 2, alpha 3, alpha n, which is having n minus 1 elements, be the corresponding orthonormal basis such that U of alpha I equal to something like C I alpha I. Okay. So, this implies T of alpha I equal to C I alpha I. So, this implies if I consider B prime, which is equal to alpha 1, alpha 2 and alpha n, will be an orthonormal basis for the space V equal to W plus W complement. This is direct sum of W and orthogonal complement of W. So, this implies V has the required basis. So, we have shown here that the inner product space V has a orthonormal basis consisting of eigenvector of the operator T. So, we have shown for these self-adjoint operators, but we have not shown what will happen if we replace the self-adjoint operator by normal operators. So, these questions we will answer in our next lecture.